All right, let's begin. So our seminar speaker today is a super person, is Dr. William Linch. He was a professor at Chile and then moved back in the States and got invited by the Beckers at Texas, and he's working on 11-dimensional supergravity. So William, you have the floor.
Thank you very much. Thank you for the invitation. Let's see. So this is a big project. It's actually a whole proposal that has lots of parts, and everything has to be done separately. So this has been going on for, I guess, almost 5 years or something. And it's work with the Beckers and Daniel Butter and Sunny Guha and Stephen Randall, who used to be a student at Maryland, Daniel Robbins and Anino Sengupta. And also some of this, I'm also working with another student here, Artem Bolshov, but he is, this is not specifically about that work, although I will touch on it a little bit. So the motivation is that, so we have this string theory or M theory, as people, whatever you prefer to call it, it promises to be a calculus for quantum gravity. But the foundational principles are still obscure. So, you can call it string theory, but that's very misleading, as we now know. And there are lots of properties of our formulation that are known to be not fundamental. So we know how to get some stuff, but we don't really know how to formulate the theory from first principles. So, for example, background dependence and the fact that it's not any one of the string duality frames is not S duality complete and stuff like that. So, or even T duality complete. So let's just say U duality in general. So that's not supposed to be the case. So, if you have an M theory, which is supposed to be the entire web of everything, the whole thing put together, the entire U duality orbit of any particular string theory, then this thing can have some stuff that we don't know how to describe properly, mostly because the brain picture requires you to do things that you don't know how to do. For example, the 2 brain and the 5 brain are simultaneously light or heavy, so you can't just turn things off and try to quantize one object. So, but in any case, we know that this thing exists as a theory somehow, and it must have some low energy effective action. And when you have this low energy effective action, it'll be manifestly background independent, and because it doesn't specifically refer to the formulations a la the p-brains that you were using to understand where you're getting this thing in the first place. So how can we get an effective action if we don't even know of what? So, that's probably why we're staying under the light, because we don't really know what goes on in the darkness. But there's actually an example of this that has happened in history, and that is the Born-Infeld electrodynamics. So in this case, they argued that a fundamental theory should not have unbounded energy densities, and the Coulomb potential is in that way problematic. And so they just tried to construct something that has the property that it looks like Maxwell at low energy, but the Coulomb solution is not a solution, and the energy densities are supposed to be bounded. Now, in principle, that's nice, but you may not expect that to have anything necessarily to do with a fundamental theory. But we'll talk about how this is actually an example of a consistent truncation, so that any solution to this theory would automatically be a solution to the theory that has derivatives, even higher type derivatives than the ones that they included. So they wrote down this Born-Infeld, which is nonlinear electrodynamics, with this property that they wanted, that the Coulomb singularity is no longer a singularity. So then people said, well, but that's nice, but that's not how the world works. It's QED, and we have to do quantum corrections in perturbation theory and so on. And then, of course, the problem came back as ultraviolet divergences. And so Now you go off and try to figure out how to fix that. And in the end, let's say, this is my cartoon of history, motivational cartoon. Open string field theory fixes these problems, but of course, then you go and check the low energy effective action, which Metzev and Zeitlin did, and they find, yes, that's the Born-Infeld theory. So this is actually a remarkable thing to me that, 5 decades before before the discovery of string theory and the subsequent process of trying to compute its low energy effective action, that was already guessed on by some people who had no idea even about the foundational properties of quantum field theory. So the question is, can we do the same thing for gravity? Now, of course, that was immediately thought of and tried, but we don't really know what same thing means. So for example, one thing you might want to say is, well, it should have no space-time singularities. Okay, so that was the analog of the Coulomb potential. But that may be too strong. Maybe that's not the right criterion. And in any case, it's very hard to use. If you have to start guessing from solutions what the effective action should look like, you're going to have a hard day. So another thing could be like, well, maybe this characteristic form of the square root of the determinant is the right idea. Well, it seems a bit artificial. Why is that the right form? What we know is that it should be a characteristic class of some type, but why that one? And in any case, it has ghost problems, right? So that was never. People have tried this kind of thing quite a bit. Maybe self-dual, Born-Infeld self-dual. Schrödinger knew that, right? So, but self-duality doesn't fix the Born-Infeld Lagrangian, and so it's too weak of a condition to get a unique answer. Although it's a nice start, right? So you can try to use this to check some properties. And then something that I didn't hear for a long time until later is that actually Born-Infeld is the only nonlinear electrodynamics in 4 dimensions that doesn't birefringe. The 2 polarizations of light propagate at the same speed in any solution to the theory. Okay, so that seems pretty important. In fact, people argued that should be the property of any theory that has a fundamental description, because how are we supposed to quantize a field when the 2 polarizations won't even stay in the same package? So this is something. Anyway, this is very hard to use in dimension greater than 4, or it's vacuous, I guess, because the polarizations sit in the same multiplet. So, okay, what about extended supersymmetry? Well, that's actually an interesting possibility, okay? So what happened, Bagger and Galbraith have shown that if you start with, essentially they've proven the following statement, that if you start with Maxwell action and you add the first irrelevant deformation, and then you impose that it has n=1 supersymmetry manifest and nonlinearly realized n=2, then you uniquely get the Born-Infeld action, okay? So specifically, take the 40 n=1 vector multiplet as to be the gold stone for partial supersymmetry breaking from n=2 down to n=1, and that will give you uniquely the Born-Infeld interactions. Okay, so that sounds promising, right? Well, can we do that? So let's try to generalize this Born-Infeld result, right? So the proposal is, what's the analog? Well, it should be something like take the Einstein-Hilbert and add add the first higher derivative correction, and then supersymmetrize. Okay, can we say something about the low energy effective action based off of this kind of observation? And this is not my idea. Like, this is Green and Pearl and guys like that have a long history of pointing this out, that this is expected to be true. But it would be true in the one case where you expect it to be unique, and that is the 11th dimension. Excuse me. And as far as I understand, this is related to the fact that there are no matter representations to cause any non-uniqueness. So, but if you do this in components, then you have an infinite Noether procedure. And it doesn't really even matter that it's infinite, because the first 2 orders are already not understood. So, it's completely impossible to, well, people have not been able to make much progress in this regard. component analysis. Now notice it has to be infinite, right? It needs to be infinite because if you expand Born-Infeld out to any finite order in the field strength, it will have the Coulomb solution as a solution, but that's not the statement, right? So it's a non-perturbative effect in the field strength that we're looking for. So you need to go to all orders. So, well, let's do superspace, right? Because that's what that's for, isn't it? Well, of course, right? Because you can't do superspace off shell in 11 dimensions. It has too many supersymmetries. And so the problem here is that you need to reduce the representation, as Hazel and Youngrui will tell you, is huge if you just take an unconstrained field, and this is completely not the right representation, so you need to cut it down. But the problem with that is that the constraint that you need to impose is not integrable, or at least we don't know one that is. We don't know a formulation where the constraint can be posited in such a way that the representation is irreducible and still not constrained by equations of motion. But there's a proposal to get around that. Also, not really my idea, although we didn't know it at the time. But we rediscovered some ideas here. But you can reduce the structure group and solve the constraints. So I guess in a sort of traditional way, one of the ways you could say that is light cone does that. Right? If you do a light cone analysis, you're reducing to the little group, and then you're organizing your analysis according to the representations of the little group. So okay, and then if you can do that, you solve the constraint. Now you have an unconstrained field, and now you can use that field to write an action. Okay, so let me give you an example. This is one that seems like pulled out of thin air, but it's actually relevant to this project. And that was an idea by Perry and Schwartz of how to solve this problem in the case of a gauge 2 form in 6 dimensions. So a 2 form in 6 dimensions has a 3-form field strength, and the Hodge operator takes 3 forms, and in 6 dimensions in Minkowski space, it squares to 1. So the generic 3 form is reducible, and so you have to split it in half, and that's the problem. Okay, you gotta this is the analog of the chirality constraint. You need it to only have half of the naive number of degrees of freedom that you would get from a 2 form. So, but this is not integrable, because if H is the curl of a 2 form, then this is going to give you the Maxwell equation. Right? So it forces you into this problem, right? So this is the famous problem, the problem of the chiral 2 form, and in fact, it's a problem that crops up everywhere. One of the themes of this talk is that this stuff touches on lots of problems that are familiar from other angles. So what the next proposal was to reduce the structure group and solve the constraint. So you take 5 dimensions, or 6 dimensions, you split it into 5 plus 1, and then you reduce this 2 form to a 2 form in a vector, and then you solve the constraint for the vector in terms of the 2 form. Okay, now you just have a 2 form. The vector is determined in terms of the 2 form. You can forget about it, and you just write something down in terms of the 2 form. And so there's something like this. This works. So you can check that Perry and Schwartz, I forgot to write a reference for that, but Perry and Schwartz, they used this to write down a Born-Infeld-like theory for this 2 form, for the chiral form on 5 brane. But this is the linearized version, and it's very easy to check that even though it's not manifest, it actually has a non-linearly realized Lorentz symmetry in 6 dimensions. Okay, Poincaré symmetry effect. Any questions about that? Because this is sort of what the idea is in general. We have to do this in a very complicated situation, but so let's try that. So the first idea is to embed 11-dimensional n=1 supergravity components into that's a frame here and a gravitino and a 3 form, this famous fact. And you want to embed this into families of 4-dimensional super-Poincaré representations, and I'll explain. It'll be well, let me just say in words now, why 4 dimensions? Well, because that's the easiest one. You know, that's the one that most of the books are written about, most of the phenomenology literature is about. And it actually, more to the point, it's the largest amount of super-Poincaré that you can have and still have all of your representations with a finite number of fields, okay? So you get a whole bunch of components and they're all mixing into each other under supersymmetry transformations, and you get these pictures that are, this is my attempt to draw the pictures that are so familiar to the local crowd at Brown, but it's this is the cartoon of the spectrum that we need. And then once you have that, you what's going on behind the under the hood is that there's some super geometry that you're splitting by reducing the structure group from the super-Poincaré group of 11 dimensions. You're reducing it to a smaller structure group, and then you're solving your constraints with using the fact that you've broken down the structure group, similarly to what we did, what I showed you for the chiral 2 form, okay? And then you have the analog of the unconstrained 2 form left over, and you build an action out of that thing, and then you show that it has all of the symmetries, right? So so the next step is you construct a 2 derivative action from the manifest symmetries, is what that should say. and then you try to make it invariant under the non-manifest symmetries. So I'll return to this action. I'm just throwing it up here now, so you'll see that there are actually things behind everything, all the words that I'm saying. So then you construct an 11-dimensional supergeometry, the one that you already solved, right? So the amusing situation is that we have the answer, we don't have the question. And so I'll come back to that. And then you build this up, and with that geometry, you can now construct the leading deformation, because the geometry tells you what the Einstein, or what the curvature 2 form is, and what the torsions in the superspace are, and things like this. So then you try to construct the Riemann, or the curvature 2 form more specifically. And then with that thing, you start building up the first Pontryagin class, and also the X8 invariant, and so on. Right? So that's what you're going to try to do. And then after all of that, you integrate out the auxiliary fields and study solutions, okay? So this reminds me a little bit of that South Park joke about the gnomes. But that's not, I don't know how to say how to do that yet, 5 and 6, because we haven't finished 4, but there's already something to discuss, okay? And like I say, please stop me if you're not afraid of hearing your voice on YouTube, because if you have any questions, okay? All right, so how do we do all this? We need some technical stuff, right? So let's do some supersymmetry. So this is the famous relation, right? You take 2 supersymmetry transformations, and then as a superalgebra, they close on the translations. So you start with an action which is supposed to have some symmetry like this, and you write down some bosons and some fermions, and these Q operators are fermionic, so they take you from bosons to fermions and vice versa. And when you do all of that, you write down a symmetry of their thing and of your action. You can show that this action is invariant under the transformation that looks roughly like this. And then you compute the algebra of this transformation, and you find that it doesn't close. So there's a translation piece, which I thought I had fixed the notation for, but this is supposed to indicate the translation piece. And then there's this junk here, okay? So this is not a linear representation of that algebra. Okay, that's, you can qualify it however you like, but it's simply not an honest representation the way a representation theorist would talk about it, okay? So that means that there are going to be problems. For example, all of the things that you can normally do with the fact that it's a linear representation, you cannot do anymore, right? But why you not hear about that so much? Well, this thing is a trivial symmetry, this thing that it generates here. This is the part I learned some things from conversations with Konstantinos. And so it's trivially a symmetry essentially because it's generated by the action itself. So if you take the bracket, Poisson bracket of the action with itself, you're going to get 0. So that's going to be a symmetry. And so you might try to add it to the algebra of the other symmetries, okay? So we're changing the rules, right? We're changing the algebra, But we're going to say, it's fine, you know, because we're changing it by things that don't really matter, because if you notice here, this is an equation of motion, right? So maybe that's okay, you know, and at least we'll have an honest, you know, representation. Well, that you need to change the fields if you do that. And so you can add a field, and for example, this will work, okay? And now you have a symmetry that closes. You get exactly QQ equals P, and it happens on phi and psi and F, and you don't have any other conditions, right? So you get exactly just the first term here on the right-hand side. All right, so that sounds great. Oh, we need to change the action, right? So we need to put this thing in the action, otherwise we're not allowed to use it. But it's trivial. You add it, you can see here, you're adding it algebraically. So if you integrate it out, you don't get anything interesting, okay? So there's a way to fix this. Now, that's not necessarily going to work, right? So nobody knows how to do this problem when you get higher than 9 supersymmetries or something, right? So you don't know how to add the fields. Already when you look at generic representations with 8 supersymmetries, then the number of fields you need to add is infinite, and things like that. So well, I said generic representations. I'm being very careful. I want all of them. We need to be able to make any of them, right? So, all right. So this thing that's acting sort of so trivially is called an auxiliary field, but the auxiliary field is precisely what's allowing you to claim that your representation is linear. This is just really a representation. All right, so here's the one of the stuff that's familiar, right? There's a chiral superfield, which consists of a complex boson and a Weyl spinner and a complex auxiliary field, and they fit together in a thing like this. And this diagram is not so easy. I stole this diagram from a paper by Corey and Jim, but so it came out a little bit hard to see. But this is the representation for that. These lines are showing you where the components go. So there are 2 components here because this is complex. This thing here has 4 components, and then this thing here is also complex. So there are 2 components. And you have a similar one for another important representation with, another important representation, which is the real superfield. And that's the picture in the top right here. So you can just follow all of the transformations around and see where they go. And we'll come back to that, okay? That's not just lip service. We have a similar situation where we're going to take these guys and we're going to package them in a way where we stick them in these nodes, and then we have other transformations moving us between the nodes. Okay, so and those will be the non-manifest symmetries. All right, so that field D here is auxiliary, and this field is irreducible provided there's a gauge transformation by chiral field lambda, which is similar to this one. And you can remove all of these guys, and so those are all pure gauge. Okay, so that's how you get an irreducible representation that describes a vector multiplet. It has a vector, a spinner, and a real auxiliary field. This one has a complex scalar, a spinner, and a complex auxiliary field. Okay, so now we have linear reps. That's great because now interactions are anything, right? Write down anything you want. So you need it to be supersymmetric and gauge invariant. So we have some requirements, okay? So the supersymmetry we're going to fix by jamming all these guys back into their superfield. Another way of thinking about that is you're taking that whole diagram and you're always keeping it together, right? So whatever you do with that diagram, you do it with the whole diagram. And similarly for the chiral field, gauge invariance here means that you have to hit this object with a bunch of derivatives to pull out the component I previously called lambda, and then what appears above that, this different diagram for that, and what appears above that is the field strength of this thing. So so that's how you do that for the gauge field, and then for this minimal coupling prescription. So all of this is textbook stuff. And then the point of this story is that you now write down an action, and this is it, right? So that's allowed. You don't have to check whether it's supersymmetric or anything. It's automatically allowed, and that's what a linear representation buys you. Okay. So corollary of this then is automatic, that the target space for Fourier equal and sigma model is a Kähler manifold, and the Kähler metric is the Hessian essentially of this Kähler function. All right, so another corollary is that the superpotential is a holomorphic section of our Hermitian line bundle over the Kähler base. That's a lot of nice math talk for it's this thing, W of phi, right? And then the gauge kinetic function is also a holomorphic section, but it's a map from bilinear forms on the gauge algebra. So over the Kähler base, okay? That's because in principle you could have multiple gauge fields here, and then this thing would have to carry. Would have to be the dual of the tensor product of that representation, right? So that's all automatic because the representations are linear, and the action we're going to see is exactly using this structure. This is just fixed by superspace rules. Well, it's called superspace rules, but it's really just the fact that it's off-shell supersymmetry. All right, so now you integrate out the auxiliary fields, and what happens? Well, this is like, this is familiar from from resolving the Fermi interaction, right, with a heavy field. When the heavy field is so heavy that the kinetic part doesn't matter, you can just integrate it out and you get this kind of picture. And so you're going to change the interactions. So the interactions here are all happening nicely, and now you're going to integrate out the intermediate field and get some more complicated interactions. And so here are this is what happens. So the auxiliary fields in this case, you get some explicit formulas, and then you put them back in here, and as you can imagine, you get very complicated interactions, right? This is a nonlinear function, this is a nonlinear function, this is a nonlinear function, and all of that gets put in there, okay? All right, now extended supersymmetry. Well, let's see this in action, right? So this is a famous example that I think a lot of people, know, is this 4D n = 2 vector multiplet. And Seiberg and Witten did something with that. So in this case, you split it up into n = 1 representations. You get a vector multiplet and a chiral multiplet. And then you put a non-manifest. The non-manifest symmetry is going to mix the two, right? So it's going to take the spinner into this f term and then the derivative of the other scalar and things like this. And so you just write down the only thing that's actually, this is the only thing that's allowed up to normalization, right? Because this has to be chiral, and this has to be chiral and also reduced. So there's a technical thing, and that fixes this transformation. And then the effective action is completely determined by this meromorphic section of our Hermitian line bundle, because the Kähler term has to be fixed in terms of, I changed notation for some reason, sorry. Oh, no, it's fine. Tau is the derivative of tau is the function we had before. And that's just from imposing this symmetry in addition to the off-shell n = 1, right? So you're reducing the Kähler interaction to just be determined from the holomorphic interaction, okay? So that's what n = 2 buys you. And Seiberg and Witten exploited this to great effect by finding specifically what tau is for n = 2 gauge theories, okay? And this is a picture where I'm showing you how you take those diagrams that you keep them all together and then you attach them to each other. I stole this from Young or Hazel or somebody's paper. This is supposed to be taken as a schematic. I don't really even remember which representation that is, but you put these things together in lumps of things that are connected by the second supersymmetry. Okay, and that's what I'm trying to show with that picture. So it's amazing. You get the leading low energy effective action of 4D n = 2 superangles, right? I mean that has all of this physics in it, and like confinement, a chiral symmetry breaking, and everything. It caused a huge revolution, right? So and that's just from manifest n = 1 with a nonlinearly realized n = 2, and then some knowledge about the holomorphic properties of this current function. Okay, so we're going to see a lot of analogies. So how do we apply this? Well, there are no matter representations in 11-dimensional supergravity. And the interactions of matter representations, well, what are they going to be? Well, those are higher derivative. They're just higher derivative terms, right? So you can think of higher derivative terms as interactions. So for example, it's known that the leading correction is Riemann to the 4th for M theory. This has to do with the 5-brain anomaly. This term here has to do with the 5-brain anomaly, for example. And so there's the M theory 3 form, and it's wedged with some 8 form, and the 8 form is 4th order in the curve. I wrote Riemann, but I'm using Riemann and curvature 2 form interchangeably. Okay, So it's actually curvature 2 formed to the fourth with something done to the Lorentz indices to get rid of them by some famous tensor called T8. So there's a whole bunch of stuff there that you're going to use as input, right? You know that the first higher derivative correction to M theory is that object together with all of its supersymmetry transformations. Okay, that's the idea. So then supersymmetry, because of that, this is a higher derivative interaction. When you impose supersymmetry, you're going to get something that's not polynomial in the Riemann tensor. Okay, just like in Born-Infeld, it goes on forever. So the question is, can we look for the supersymmetric orbit of this X8 term, right? That's the idea, and it's like I said, this is like green gut pearl, people like that, and so you know it's impossible in components, but it's trivial in 11D superspace, except that you can't do that because you need an off shell, and there isn't one, right? So let's compromise. That's the idea. Okay. So that was just a review of where we're going. So the strategy now is going to be embed these components, like I said before. I'm just going to review. Construct a two derivative action. Now you see here, this thing is going to be like the Kähler term, and this thing's going to have Kähler pieces in it, but it'll also have the only superpotential type terms. I'll explain what these pieces are in a moment, and then I'm just reviewing now what we were going to do, what the plan was. Okay, so you then use constructed geometry so that you can build the first deformation of this action, so the R to the 4 guy, and then that's what you're doing here. So I'm writing down here what the beginning it looks like for that deformation in some language that I didn't explain, but I'll explain a little bit. Okay, and then you try to integrate out the auxiliary fields. All right, so what we need is an 11-dimensional superspace that looks, the supersymmetry thinks it's 4-dimensional. So this is 1/8 of the total supersymmetry. Now, in order to do this, this base space here turns out to have to carry a G2 structure. Okay, so many people call this almost G2 structure. I'm trying to say the weakest possible thing, right? This is very, very far from holonomy. Okay, so the n=4 chiral subspace already requires there, for this problem, that there be an almost G2 structure, or a G2 structure, as Bryant calls it. And that's a 3 form that is sufficiently sort of generic in a way. So I don't know if I'm saying the right words, but basically the idea I'll explain in a minute. When you have a G2 structure, then you can build a symmetric bilinear form from that, and it will be definite. So you can pick the sign of the structure so that's a Riemannian metric, right? So almost generically, a 3 form will give rise to a Riemannian metric. The not really quite generic statement is an open condition. The open condition is that this metric that you build has to have non-vanishing determinant. But saying that some specific polynomial of the entries is not 0 is relatively weak, right? It means that if you find anything where it works, then there's an entire neighborhood where it works, right? Because it's not a closed condition, it's an open condition. Okay, so then if you want to talk about 4D n = 1, why G2? Well, let's see. Well, if you want to talk about 4D n = 1 solutions, which we're not going to do, right? We're going to keep everybody 11-dimensional. But if you were to compactify down to 4 dimensions, then you may expect that, from Witten's results and so on, that if the space is simply connected, compact, and has G2 holonomy, then the space-time will have n = 1 supersymmetry, right? So this is related to the fact that we're using n = 1 in 4 dimensions as the fiber space here in this fiber bundle. Okay, so there's some lots of excitement recently in the mathematics community because there are some first constructions of compact G2 holonomy manifolds. We won't need any of that because we are not doing that, right? This requires that this 3 form here be closed and co-closed, and that's very strong. Those are very strong conditions. Okay, so our space is almost generically Riemannian. So that's what we need. All right, now. When you have that, that's necessary for the scalars that you get from splitting all your fields into 4 + 7. but you're also splitting this 3 form into 4 plus 7, and you're going to get a 3 form, 7 2 forms, 21 1 forms, and 35 more pseudoscalars, right? And these are all coming together, like they have gauge transformations that connect them. And this gives rise to something called a non-abelian tensor hierarchy, which I will briefly review ever so briefly. And so this gives us, this is what I just said in words, okay? So this symmetry, this tensor hierarchy is a hierarchy of representations of the diffeomorphism group in 7 dimensions, right? Diffeomorphisms acting here. And so these guys are all charged. And so there's a gauging by diff y, and you get a non-abelian tensor hierarchy from this collection of forms. And such objects always, it's a differential complex, they always have Chern-Simons type invariance if you're in the right dimension and whatever other very weak conditions. So we can use that. That's the first thing we build, okay? So let's look at that for a second in a little bit more detail. So Jim actually is the first one to write down the de Rham complex in 4D n equal 1. This is what we need. We have chiral fields, the scalars, and then the 1 forms are the real linear field that we talked about with a chiral parameter, gauge parameter. Then the next one is a chiral spinor field with a real parameter. And the next one is a real field with a chiral spinor gauge parameter, and so on, okay? So you stick all these guys, you glue all these guys together, and you let their gauge transformations mix them. So whenever you have such a situation, it turns out you can splice it with another differential complex provided, and then there are a list of rules, okay? So these rules were actually originally found from taking gauged supergravity theories and asking what is the structure of all of these, vector multiplets that you're encoding when you have a gauged supergravity. Okay, so you have all these maps. So this Q is essentially a differential along some complex of representations. This is another copy of this complex with the same differential, and then the downward maps T are the action by some non-abelian algebra. And then H we'll get to in a minute, okay? So if you require that the gauge transformations close on a basis of fields on your complex, then you get 3 conditions. The first one is just saying that T's form a Lie algebra. The second one is saying that the Lie algebra action on the complex is natural, okay? So G equivariant, if you know what that means. And then H is another interesting condition I won't go into. But that's not enough. You don't just want closure. For what we want to do, we want to be able to build field strengths. And I didn't know this when I first worked this out. I didn't realize that there's a whole condition that comes from that. And there are actually entire, one of the famous problems in other theories that are related to this, like generalized geometry and string field theory, is that you don't have enough field strengths. Okay, so we need the field strengths to exist, and this requires that Q be a differential, and that H, that the action of the Lie algebra be homotopically trivial, right? So it means it's Q exact in the sense of this diagram commuting, okay, with H's. And then H, if you pick any particular element of the Lie algebra, then H squares to 0, right? So it's a differential again for any element of the Lie algebra. So what's an example that we all know, even though you don't recognize necessarily what I'm saying? Well, when the algebra is the diffeomorphisms on some space, then Q is the de Rham differential, and T is the Lie derivative along the vector field. So the algebra is the algebra of vector fields, right? So, so in this case, you get a Lie derivative along vector field, and then this H is the contraction with the vector. And then this formula here is Cartan's famous formula. So another thing I learned in this process is that the action of the Lie derivative is homotopically trivial, right? So of course you know that, but you don't necessarily realize. Anyway, so this is the structure, and this structure gives rise to, because it's just differential forms, it gives rise to a Chern-Simons theory, or Chern-Simons invariant, and so on, and so you can just write it down. So that's going to be the first part of our action, okay? Well, you don't just write it down. You do a lot of work, and then you can write it down. All right, so in addition, there's going to be a volume invariant, but this thing here is the thing I just described. This is basically C wedge F, or C wedge G, where G is the derivative of C, but written in superspace. And all of these guys here are the unconstrained fields that are holding all the other guys in, all the component fields for the 3 form. So this action is, and then the only thing you can add to that is a volume term. And by the superspace rules, 40 and 70 symmetries, you can only write down what I wrote here, okay? So it's all up to one unknown function of one variable. This sounds familiar? Okay, so what's this variable? It's essentially the metric on the space of tensor multiplets, where by tensor is, always in quotes, people always mean the 2 forms. And so this is the notation here indicates that it looks like a 3 form from the 4-dimensional point of view, and from the 7-dimensional point of view, it looks like a one form. I'm saying 3, but I'm doing this. I should do this and this, right? And then if you together they add up to a 4 form, which is what this field strength is supposed to be. Okay. So extended supersymmetry now fixes, you get a condition again, the way Seiberg and Witten did, and it fixes if you make this, so f becomes, y here, and y is something that looks like a Legendre transform. In fact, it would be a Legendre transform if f were convex, but it's not. So, and we don't know that yet, but you find out. And then this thing, the formal Legendre transform, satisfies a polynomial equation of order 4. Right. So you have this kind of solution, this kind of weird object. So you can write down an explicit solution for this, which is hideous because it's a quartic, but you can, and then you can integrate it, and you get something even more hideous, which is still closed, closed form, right? So you get a closed form non-polynomial action for the variables. So that's all very familiar. I mean, Yang-Mills is also like that. Okay, so that's basic. Oh, I was going to say a little more about the action, just to give more details of what all the players are. So the psi over here that I don't see because it's under Konstantinos is the gravitino field. There are 7. We take in this splitting, there are 32 gravitini, and we took 4 of them and we put them with the n-equal with the graviton for the 4 dimensions, right? So the other, 28 is 7 gravitino multiplets, because each of them is going to carry 4. 4. And so you have 7 of these characters, and so this guy looks like a scalar. Oh, it's a spinor on space on 4 dimensions and a 1 form in 7. Okay, and then this is the collection of the tensor hierarchy prepotentials. So it starts off with a chiral, and then it has a vector, and then it has it starts off with let's see, if I start at I equals 0, I get a 3 form, which is a real field. And if I go to I equal 1, then I get a 2, 1, 2, did I write this wrong? I get 2, I get 7 2 forms, which is chiral spinors. And then if this is 2, then I get 21 vectors and 35 chirals, right, again. So the G's here are just their exterior derivatives. But when I say all of this, it's actually doesn't look that pretty in explicit notation, as people, some of you are quite aware. Okay, so and then this guy here is interesting. The guy who looks like a 4 form in space-time and a scalar on the internal space, let's call him G. That's actually doing the double duty as breaking down the conformal, the scaling symmetry in the 4-dimensional superspace. So it's called the conformal compensator. Okay, so it's doing double duty as the conformal compensator. And this guy F is actually very closely related to the field strength that has 1 4-dimensional index and 3 internal indices. But its lowest component is 35 scalars, and the 35 scalars are actually the G2 structure 3 form, right? So it looks like a 3 form on the internal space. It has IJK type indices. So this notation is hard to understand because I'm not writing explicit enough formulas, but this thing carries the field strength for this kind of rep, but it also carries a scalar, and the scalar just has like 3 y indices, so it's actually the G2 structure 3 form. Okay, so, and then this G here is just the associated metric determinant, and then of course this thing is the super frame. So this is the 40 volume piece. This is a 7D Riemannian volume that is constructed out of the G2 structure metric, and then it's all up to this unknown function that we've just described. Okay. So now you want to add higher derivative corrections. So you want to deform the action by Riemann, sums of Riemann to some power, and we're going to do this. To do any of it, you have to do it in steps. So how do you have to get Riemann and then Riemann squared, and then let's say Riemann to the 4 or whatever, right? So we actually start with Riemann. We need, how do you do that? Well, you need supergeometry. Well, you don't need supergeometry, but you're going to make your life very hard if you don't use supergeometry. So how do we build up the supergeometry? The amusing situation is we have all these prepotentials, but we don't know what the tensors are. Okay, so if you, in general in supergeometry, you're talking about a connection. It's the usual business, and that defines the torsion and the curvature to form through this relation here. And then what you generally do if you open Wesson-Bagger and you go far enough into the book, it tells you, okay, now just take these constraints and impose them, set low dimensional torsions to 0, and then solve the Bianchi identities, and you're going to get a unique solution for T and R. Okay, so that's a lot of, hitting the I believe button, but you can actually do it explicitly if you take what they tell you and you do turn the crank, then you will get the right answer. The question is, how did I know where to start, right? These things, they come from the Egyptian darkness. So, but okay, we'll get back to that. And then when you're done with that, you're going to get conditions on T and R, and you can solve those and you get prepotentials. So the point I'm trying to make here is that the prepotentials are the solution to this problem. But we already know the prepotentials, right? So we should be able to go backwards. So what's going backwards? It's actually a structure of a differential graded algebra. You start with the prepotentials, and then you start hitting with all possible derivatives and taking all possible combinations, okay? So if I just have one field, for example, this vector multiplet is some unconstrained real field, and I just start hitting with D and hit it with D again. If I hit it with D 3 times, I get 0 because D cubed is 0. It's by the supersymmetry algebra. And you have, of course, the D bars. And then you could do a D and a D bar, or a D bar and a D, and that's where the vector sits. And if you keep going, you're going to get the vector multiplet field strength. And then if you go as high as you can before starting to generate 0, you're going to get the curl of this A, and you're going to get the auxiliary field. Okay. Now, if you go, I wrote 0 here on the sides, but actually what happens is you start generating derivatives of the fields you already have, A and W and F. Okay. So, all right. So what are these guys? Well, the compensators, they all shift. If you recall, those things could be removed by the gauge symmetry. So compensators have the property that they shift, like Stueckelberg's. Okay, so you can remove them. The gauge potentials transform into space-time derivatives. So that's what the frame and the gravitino and the 3 form do. But then you also have invariants. Okay, so the field strengths in 11-dimensional supergravity, those are the 4 form curl of the 3 form, the gravitino curl, and the curvature 2 form. All right. And then there's auxiliary fields, which in this diagram is just D, but in general, we don't know what they are for supergravity, right? Because knowing that would be providing an off-shelf formulation. Okay. And then there are going to be other relations in there that are not 0, but they happen to be exactly the right type that relate auxiliary fields and field strengths in exactly the right way to be equations of motion. Okay, but we don't have an action at this point. It just happens automatically. It just generated. Okay. All right. So what are the results? Here it is. So I'll unpack this for you. Right. These are all the fields we talked about. This is the field that carries the physical fields that are inside of this representation. The most important part are written here. So I've linearized everything. So I've switched to the graviton. Okay, linearized graviton. And the linearized spin field, gravitino, sorry. And these indices, all the indices on this slide are 4-dimensional indices and 7-dimensional indices, okay? So this guy is important because it carries the graviton. It carries the n = 1 graviton. This guy is important because it carries all the other gravitini. This guy is important because it carries the KK field. This guy is both the 3-form and the conformal compensator, if you recall, compensator down here, G. This thing here is carrying the 2 forms. This is the complex, by the way. I wrote it the other way before, right? But this is the chiral and then real and then spinor chiral and then real and so on, right? So going that way. So this guy here is the 21 vectors with their attendant vectorinos. And this is the chiral guy. And this is where we use the G2 structure, right? So there's the 3-form piece. Then there's the other part, which is the lowest, this is the lowest component of phi, but it's the real part of the lowest component of phi. The imaginary part of the lowest component of phi is the G2 structure. And the fluctuations of the G2 structure are exactly giving you the metric on the internal, on the y directions, okay? So you get that. Then this is these are the other, what is it? They're all really components of the 11-dimensional gravitino, but from the 4-dimensional point of view, they just look like gauginos, okay? And what's really happening is that all these guys are mixed up everywhere, and I've picked the nicest way I can show you. There's a gauge in which what I'm saying is literally true. So that's what I'm presenting here. Okay, but because these guys are off shell in 4 dimensions, they all have their auxiliary fields, and that's the next line, right? So this guy has the famous vector auxiliary field of 4D supergravity. I'll explain in a minute what happened to the other one. This guy is a mess, right? Jim is an expert on this guy. It's a mess. It has a whole bunch of auxiliary fields in it. There's a dimension 1/2 spinner. There's a complex vector. There's a 2-form, and there's I should have written this with AB indices, but this is symmetric bispinner, which is the same amount of stuff. And this is the dimension 3/2 auxiliary, and I'll talk more about that in a second. Then there's a D-term auxiliary for the KK field, because it's just a real vector. There's this auxiliary field for this 3-form multiplet. And then, and this guy is interesting. It's got no auxiliary field. It's the only one. And then this again is D-term type. And then this is the only chiral field in the theory that has an auxiliary field. And so this is the only F-type auxiliary. So the chiral and the reals and all that, that's the picture, that's the stuff I was showing you before, right? Where you have this expansion and you can identify what the fields are. It's just that everything now has additional indices attached. Okay, so you can add up what are all these things. So if on shell, of course, you can count them, and you get, well, actually, I always forget these numbers. You get 128 plus 128, right? This is the famous on-shell multiplet of 11-dimensional supergravity. But then off-shell, you get all these contributions. So even the gauge fields change their off-shell counting, right? That's the whole problem, right? So you get more. You don't get 2 gravitons, you get 6, right? And then there's 4 additional guys from the auxiliary field, and that's that. So it's all color-coded, and if you sit down and calculate what all these numbers are, then you know, lo and behold, you get this number here. It's 376 and 376. Now, I don't understand specifically, I have an idea, but I don't understand specifically why 376. But the fact that they had to match was automatic, okay? So they match now. So at least I can have, it will not be a representation of linear representation of 11-dimensional Poincaré, but it will be a linear representation of the 4-dimensional cross G2 subgroup. Okay, so at least we have that. All right, so I think I said here in words everything, but there are 4 D types from supergravity, 3-form, KK, and I wrote 3-form, but this is supposed to be 2-form. Sorry about that. And there's 1 F type from this guy, which is carrying G2 structure and the 3-form scalars. By 3-form scalars, I of course mean the things that look like scalars from the 4-dimensional point of view that came from the 11-dimensional 3-form. and then there is this mess of gravitino auxiliaries. The lambda rho, they form a dimension 1/2, 3/2 Lagrange pair. So they cancel each other in equations of motion. And then there's a complex vector and there's a two form, okay? So this is the part of the main result, right? This is the spectrum that is written in terms of unconstrained fields. Now at this point, what we've done is essentially the analog of solving the chiral two form condition for the part that looks like BAB and forgetting about the other piece. The other piece is defined in terms of BAB, and then BAB itself is completely unconstrained. Right? That's essentially what we have done here. So all these, oops, what happened? All right, so the auxiliary fields contribute no propagating degrees of freedom, right? You would expect that, but it's not necessarily clear how you prove it. So here's a little quick proof. I'll run through it very quickly because I'm really low on time now. You vary the action. Well, in this particular case, we already knew what the action was, right? So it was that thing. You vary the action, you get some equations of, you get some super fields for which, if you were to impose the equation of motion, which we do not, I have to keep repeating that to people sometimes. If you were to impose it, it would be setting these e's to 0, okay? But the point of this is that they're first order in these auxiliary fields, and so you can solve for the auxiliary fields. Now, here's an example where I'm just giving you the mess, because the mess isn't that hideous, but you can, the point of showing you explicitly what happens is that what it says in every case is either, for example, for lambda, the auxiliary field is the equation of motion. So it contributes, whenever that happens, it means lambda cannot contribute anything on shell, right? We already know what it contributes off shell, right? You can just count it. But on shell, it contributes nothing, because on shell, this would be 0, okay? So, and that's what you want to see. You want to see everybody vanish on shell, right? Because they're auxiliary fields. They don't carry any degrees of freedom. Well, not necessarily. They could just reduce. They could become equal to something that is supposed to be there, right? And the only physical field that's supposed to be there that's gauge invariant and has dimension 1 are the curls of the M-theory 3 form, right? So this is the 1,3 part. This is the 0,4 part. This is again the 0,4 part. And they're all projected using these, psi is actually the Hodge dual of phi, okay? It's a highly, yeah, so sorry. I forgot to define that before. D is another example that just vanishes all by itself. And then the F term has basically all these guys sitting inside, right? So what this means now, if you think about the auxiliary field structure, like for the quadratic piece, if it were just quadratic, then the auxiliary fields would appear squared, right? Or in lambda and rho's case, they would cancel each other. But now what that means is when you integrate out these things, you get a very complicated polynomial, okay? And we showed that polynomial gives exactly the, in another paper, we showed that it gives exactly the Einstein-Hilbert term and the Maxwell term on the space that is not part of the 4D, right? So that's actually a result that uses some serious G2 representation theory that you could find in the literature, in the math literature, because you need to see how the Ricci tensor comes out in this language. Okay, so there are some auxiliary fields missing from this list, so they had better not be independent. And we find that the Y, the chiral, the complex field inside of the gravitino, it's just trivial. The two form inside the gravitino is reducing to again, one of these physical 4 forms up to something that vanishes on a shell. And then this guy is basically a curl, gravitino curl. I didn't write it explicitly, up to something which is again vanishing on shell. So nobody here is new, okay? So that's the point, right? So that's the proof, right? So that means that on shell, these guys do not do anything funny. All right, so the supersymmetry transformations now, and I'm over time, so I'll hurry up. They're moving you through this thing, right? You start with the potentials, and you get to the spinors, and then you get dimension 1 auxiliaries, and then you get torsions, and then you get curvature 2 form, right? And so you can just compute what we have explicit expressions for all of these quote unquote component fields that are actually superfields. And so all we have to do is, if we want to compute the component supersymmetry transformation, you take this expression, you hit it with a D. Well, I say all you have to do. After you hit it with a D, you have to reorganize it so you recognize everything. And that's actually the hard part, right? But you can show that you get this answer. It reorganizes into these combinations, okay? And some of these guys look like they may be new if you're really paying attention to this talk, but actually they're not new. They're just combinations that appear the most naturally in the supersymmetry transformations. And now this guy is interesting here on the bottom because it's like, 7 times 7 is 49. So a priori there are 49 chunks here, but actually if you look at this is actually 28. I haven't defined this projection for you, but you can believe me. 28, this is 7, and these two are complex. So you get 28 complex and 7 complex, and then this thing here is the 14 projector on the 21. So it pulls only the 14 part out, so they're 14 real. And now I have to hide this again so I can see what it says. Oh yeah, so that gives 49 real and 35 imaginary. Now why is that important? It's important because the G2 structure torsion is precisely 49 real. This is how it's defined. I won't go into any detail. And the flux is the number of components in a 4 form, which is the same as the number of components in a 3 form because of Hodge duality, and that's 35. And this thing is real. So this exactly is encoding the G2 structure and the flux. Okay. And a corollary of this is that immediate corollary of this is that compactifications to 40n equal 1 that preserve G2 holonomy, that preserve 40n equal 1, they give exactly the conditions for G2 holonomy and 0 flux. Okay. So that's the point there. All right, so let me now we'll just go crazy. So let me quickly just tell you how you get the mysterious constraints that Wes and Bagger were supposed to, that they just gave you without explaining. Well, because the torsions are appearing in the supersymmetry transformations and because we have the explicit expressions, you can just compute what they are essentially at low dimension. So for example, one of the things is we had no invariants of any kind that were dimension 0. Now I know that upsets some of you, but that's this, right? So the only thing you can write down, so I said of any kind, but of course I meant non-trivial. So you can write down the constant tensors, right? That's the way you normally do it. This one up here is the usual constraint, that says that QQ gives P. And then this one is one that includes the additional directions. So that's the only thing that you can have. And then at dimension half, it turns out this is not really a trivial result, but you can go and you can check that it's possible to arrange it so that all of the dimension half torsions vanish. That's super helpful if you're ever trying to solve Bianchi identities because those low dimension torsions are murder, okay? So dimension 1 is either 0 or now we get something interesting, this. So these are the auxiliary fields or the physical fields, whatever the case may be, across the top. These are the torsions that this superspace has at this dimension. And I put little asterisks in this constellation plot to tell you where they appear. So the first chunk of this, the first 2 are just the textbook answer for these torsions, right? It says that this torsion is the vector auxiliary and this torsion is the scalar chiral auxiliary, right? So what I guess Wes and Bagger call M and B or something, right? So, and then everybody else is new. So you can find out what they are. And then in fact, if you want, you can keep going. I mean, to a certain extent you're done because the dimension 3 halves torsions are all curls of the gravitino and the dimension 2 is just the curvature, okay? All right, so let me just quickly say a summary is that, I tried to impress upon you the importance of and potential possibility of getting some insight into the entire M theory effective action. So to do this, we formulated superspace with the necessary auxiliary fields, and we constructed a 2-derivative action. We derived the linearized geometry from the differential graded algebra, and we have now initiated the construction of Riemann squared invariant. I should also mention that, sorry, I skipped a piece. Now that you have the low dimensional constraints, you can just go Bianchi doodle your way through life, right? If you really want to, you can just sit down and start grinding out the Bianchi identities because you know the initial conditions, right? A la Wesson Bagger, right? Where they, or whatever favorite book you have, where they just tell you which conditions to set, and then you just grind through, right? So this is, I think, done in most detail in, for sure in Superspace, which is of course the standard reference, and also in Buchbinder and Kozenko. Okay, so Weston Bagger doesn't have pre-potentials for gravity, so some of the stuff would be hard to follow if you were just using that. All right, so what's the wish list now? And this will be the last slide, basically. So we want to complete the construction of Riemann squared, of course, and then Riemann to the fourth and everybody else, which has been done in, this one has been done in 5 dimensions, the part that is most interesting. But it turns out 5 dimensions is sitting inside of 11 in a way that you can keep going. There are many more steps, but you can keep going. And once you have but if you have the entire super geometry, you just write it down, right? Because it's just the Riemann tensor, you just construct the thing, or the curvature 2 form. All right, so this is this top-down approach where you just take, you know what the Bianchi identities are that you're supposed to solve because you already know the conditions of which torsions vanish in low dimensions, and then you're going to solve Bianchi identities for all the other ones. Right? So that's something that people here are working on. And the advantage of that is that it can give you the entire nonlinear geometry in principle. It's not really what you start off doing, but you could in principle do that. I would like to understand this auxiliary field mechanism for higher derivative interactions, because something weird is going on where you have all these auxiliary fields in certain G2 representations, but then here comes the big mother of 70 prime in the conformal tensor for the G2 space, and that guy doesn't have an auxiliary field, right? So how are you supposed to get the right interactions for that? Now, I mean, I guess something must work, right? If you're able to write something down that has the right symmetries, then it should just come out in the wash. But it's mysterious how that's going to happen. So for example, you could already, if you want to try at home, you can start writing 10D Born-Infeld in 4+6 split and see if you can answer that question for the 8, right? So in that case, what happens is you have the 2 form on the 6 dimensions splits into a singlet, a triplet of SU. Now the group is not G2, it's going to be SU3. So you get a singlet, a triplet of SU3, the SU3 bar, and then you get the 8, which is the adjoint, right? And there's going to be a chiral field. There are 3 chiral fields in that description, so you're going to have the triplet, the complex triplet. There's also a vector multiplet in that description, so you're going to have the singlet, but then you're done, right? There's nothing for the 8. So you can ask, how does a higher dimensional version of Born-Infeld reconstruct the correct interactions for the 8-dimensional representation? I don't know the answer to that yet. Okay. The tensor kinetic function is somewhat mysterious to me, right? So this, in 11D, we got this answer, which is this curve here, up in the top left. And in 5D, you get something that looks very similar where you just put y on this side, right? The y cubed, I mean, and that looks like this. In 5D, there's a really good reason why this is true, and that has to do with the fact that if you linearize the 5D answer around a 4D background, you can choose between, I move this so I can see, you can choose between new minimal and old minimal, which are, this is supposed to be sort of the diagram for all of the off-shell supergravities in 4 dimensions. Everything generically inside of this Riemann sphere is a non-minimal supergravity, but there are special points. There are 4 special points, 2 of which are basically the same, where you have new minimal and you have old minimal, and then you have old minimal with the opposite chirality compensator. And then on the other side, you have something called virial, or, well, Nakayama calls it virial. I kind of like his paper, so I'll call it virial. But anyway, we, as a joke, when we first discovered a linearized version of it, we were calling it new minimal, because it looks like new minimal with the compensators, real compensator switched for an imaginary compensator. Okay, so there have to, in the asymptopia, there have to be 2 ways to get either new minimal or old minimal, new minimal or virial. What am I saying? Sorry, new minimal or old minimal. Sorry, they have to be able to interpolate between new minimal and old minimal, and this function that I find so mysterious is doing exactly that interpolation. Okay. Oops. And then another thing that I would like to understand, I'm working on now with Bolshov, is decoupling a two-form multiplet to get to the M5 brane theory. This was this approach that Perry and Schwartz advocated, that I reviewed, at least for the linearized part early on, for the chiral two-form. And the point, and the interesting thing about that is if you try to describe it in this kind of language, what you will find is exactly one copy of the non-abelian tensor hierarchy. In some limit. So I mean, this thing is supposed to come out of M theory, I guess, anyway. So that's probably not an accident, but I don't really understand why that's how it's happening. Right. And the other thing I really, to be honest, don't really understand is why this works at all. So we can make it work in 11D and 5D, and is that should I expect that I can make it work in any dimension? You know, so stop here. Thank you very much. Oh my God, I went way over. I'm really sorry, guys.
Thank you, William.
Close to this, man. You need to.
That was amazing. I didn't want to cut you. That was I enjoyed it so much.
The tense thing was supposed to be a joke, but I guess I did.
Yeah. Okay, so let's thank William virtually for his amazing presentation. Appreciate it. And please. Ask any questions that you have now.
Did you, were we going to do something, discussion afterward too, or is that?
Yeah. So, right. So we'll stop now so people get a chance to log off if they have other things to do, but we'll be around, we'll stay around to keep discussing. So you're welcome to stay and join us. So are there any questions? Okay, so let me ask a question. I have the underlying question is the same, but I can ask it in two different ways. So one way to ask the question is, do you have any comments about the 376 number? You mentioned that you have some intuition, but you didn't elaborate on that.
So I don't have an intuition. I had a hint of an idea. I had a shower thought, is the correct way to say it, that I haven't investigated yet. So one of the things that happens when you construct the nonlinear version of this non-manifest symmetries is you find that there's a chunk of it when it acts on the chiral fields, the 35 chirals, right? That chunk, it actually transforms under a trivial symmetry. So it needs to. I mean, it's just, that's what you get.
Yeah.
And so because of that, you could say, well, what about that idea of just adding the auxiliary field, right? Yeah. And, you know, if you put that back in the spectrum, what happens? Well, one thing is, if you did that, it would have to be an n=1 super field of auxiliaries, right?
Yes.
It's the entire algebra. So if you do that, you're going to change the number from 376 plus 376 to something else plus that same something else.
Right.
So it
right.
will also be off shell.
That was my next way of asking the question, and has to do with the extra supersymmetries which are not manifest. So how can you be sure that when you check the algebra of these extra supersymmetries, that they don't require additional n=1 superfields?
I see. Of the non-manifest ones.
Right.
Yeah. The non-manifest ones are going to be on shell. I'm okay with that. So okay, it's not exactly like the chiral 2 form, right? Because in the chiral 2 form, the non-manifest symmetries were non-linearly realized. So that's not what's going on here, but it's similar to that in the sense that, you know, you have the solution that respects the smaller structure group, and then for everybody else, it's not going to be a representation. I'm not claiming that this is a representation of 11-dimensional super-Poincaré.
No, yeah,
other than on shell sense, you know, which doesn't really mean what the words say it means, or indicate that it means. So it's really an honest representation only of the proper subgroup.
Yeah. All right, thank you. Any other questions?
But just to emphasize, the main use of that is that this process separates the constraints, which we know in 11 dimensions to be non-integrable, right? So so it separates the constraints and solves the part that you're able to solve. And then the other guys, you have to say, well, what about those? But there we know that what they do is they put the theory on shell. So if you take the solution to the sort of nice part and you use it to construct the dynamics making an action or something, then it will automatically take care of the other ones. So in fact, at the end of the day, you have the same on-shell solution. But the advantage here is that you can use, you get analytic structures from the point of view of because the action is nonlinear and everything. And so there's actually a part of the process, for example, where Witten tells us that we're supposed to take the 4 form and shift it by the first Poincaré class divided by 4 or something, right? Because of this anomaly in the flux quantization. Yeah. If you think about what that means in the action, I mean, the action we described in components is polynomial because every ingredient that you used to write it has Stuckelberg fields in it. So when you go to West-Savino gauge, right, those fields become nilpotent, and so all of these non-linearities, they go away because of the nilpotence. That's the way it usually works with the vector multiplet, right? Yeah. Non-abelian and Yang-Mills in superspace is not polynomial, right? But if you go to West-Savino gauge, it truncates. So the similar thing is going to happen here because the fields that you're using to write the thing down are not tensors, right? But you can, if you can find out what's going on in this Witten shift, you can take all the fields I described and find out what they're shifting by, shift them, and now you're going to get, those are all now tensors. So you're going to shift these prepotential, these non-tensors by tensors, but now you have, the analytic structure was already fixed. You're not allowed to do anything else, right? So now when you expand it out, it will be unbounded in the powers of those structures. So you get higher derivative corrections forever. Already from that, just from that. So you didn't even construct the art of the 4 invariant yet.
Yeah.
So parts, I mean, it's known that parts of it will come from D-term interactions, right? So maybe those parts are automatically being generated by this shift.